Licenses and call signs. Amateur licenses are valid for 10 years. So here's your 10 years here. Okay, during that time you can transmit. At the expiration of the license, there's a 2-year grace period during which the license can be renewed without testing. So up to 2 years after your license expires, you can renew the license without retesting. But during that time, you're not allowed to transmit until your renewal is received. Okay? After 2 years, if you let it go that long with an expiration, then you have to retest. And the last time we tested here on Big Island, we had a couple of people who had let their license lapse more than 2 years and had to take the test over again to be relicensed, and they ended up with new call signs. So if you have a license, take care of it. If you don't, you can renew it during the last 90 days of the license, incidentally. So for the last 90 days here, you can send in your renewal. If you don't get it done before the expiration, you have 2 years that you still may do it without having to start over again. United States amateur call signs begin with the letters A, K, N, or W. U.S. amateur call signs have a single numeral in them. So if you're offered an answer that has more than one numeral, it's wrong. Some examples, here's an A call sign, AH6I, that's mine. Here's a K call sign, K7SU. Here's an N call sign, N7FE. Here's a W, WH6DXG. And incidentally, this was the last call sign issued in my last testing session, WH6DXG. So those of you testing here in the next week or two could end up with a WH6DX something call sign. This is what's referred to as a 2x1 call sign. This is a 1x2. You have one letter, the numeral, and then two letters. A 1x2, and this is a 2x3 call sign. 2 letters, the numeral, and then 3 more letters. Okay. A 1x1 call sign in this pattern, K5P, is a special event call sign. And they're issued on a temporary basis for a special event of interest. A station must identify at least every 10 minutes and at the end of a contact. If you're using a tactical call sign, like net control or race headquarters or something else like that, team leader, a tactical call sign like that, then you have to use the FCC call sign at least every 10 minutes. You cannot be the control operator of a station exercising a higher license class privilege than the license you hold. So if you are at the excuse me, if you're at the station of someone who is an extra class and you're the control operator, as a technician, you still can't operate beyond your technician class privileges. You can operate your station as soon as your license appears on the FCC ULS database. You do not have to wait for the paper license to come in the mail. Some operation items. Transmitting and receiving on the same frequency is called simplex operation. Transmitting on one frequency and receiving on another, as with repeater operation, is called duplex operation. The difference between two duplex frequencies, a repeater input and a repeater output, for example, is called the offset. The normal offset on the 2-meter band is 600 kilohertz, and the normal offset on the 70-centimeter band is 5 megahertz. And these are found in questions that could appear on your test. 2-meter offset, 600 kilohertz, 70-centimeter offset, 5 megahertz. A squelch circuit is a circuit that quiets a receiver while it's not receiving a signal. RACES and ARES are organizations which provide communications in emergency. RACES can be used only to support government and civil defense agencies, but both RACES and ARES are emergency organizations. In connection with the immediate safety of human life and property, an amateur station may use any means available to communicate when normal systems are not available. You'll remember that this phrase right here, immediate safety of human life and property, is the FCC definition of an emergency. Immediate safety of human life and property. CW, Morse code, is the mode with the narrowest bandwidth. All signals that are conveying information have a bandwidth. The narrowest bandwidth is by Morse code CW. Circuits and components. A circuit diagram is usually laid out so that a signal travels from left to right. And let's take a look at this circuit right here. This is a power supply. It has the power coming from the wall in through the plug here into this transformer, and then through this diode rectifier, through the filter system, and through a voltage regulator, and then the power comes out here. So you have your energy traveling through this circuit from the left side to the right side. We're going to talk more about this circuit in a few slides later. Okay, same thing in a block diagram. Again, from left to right, this is a receiver with the signal coming in the antenna going to a mixer, then to an intermediate frequency amplifier, and then to this thing right here, which you'll remember is a product detector, and then to the audio amplifier and to the loudspeaker. And then from down here we have a couple of other things that are getting put into that circuit as it passes through that chain. Here we have an oscillator that's putting a signal into the mixer. Here we have a beat frequency oscillator which is generating a signal and putting it into the product detector. Okay, so again, from left to right, and then any things that are being inserted can be coming up from below or above, usually from below. A resistor is a device that opposes the flow of current in a direct current circuit. The circuit diagram here, you'll remember I said looks like a switchback road, and you can see how that would resist the movement. So if you think of it that way, that will help you to remember that that's a resistor. Resistors can take many forms. Here are some, this is a fixed resistor, a film resistor. Here's a wire wound resistor, and what it is a ceramic core, ceramic tube that has resistance wire wrapped around it to make the resistance. Here are the connections to it. Here are mounting tabs. Here is an adjustable wire wound, and this one has another sleeve on it that can be moved to adjust the resistance. So if I have something hooked to here on that tab, I can adjust the amount of resistance from the ends of the resistor. Okay, here is a carbon resistor, very common type. This would be a resistor array in an integrated circuit package, so you'd have a bunch of resistors in there, probably 8 of them or so, at least. Here is a wire wound similar to this, similar to this one. It's actually adjustable, and it's arranged in a circle so that I can have a shaft here that I'm turning this wiper instead of having to move it along here in a straight line. I can actually have that hooked up to a knob, and I can move the wiper around the resistance wire. Here's a similar thing. These are typically very small and mounted on printed circuit boards. The resistive element is this black layer that you see under here, and that connects to this side and this side. So that would be this side and this side of the resistor. And right here you have a wiper that rubs on that. And I can take a screwdriver and put in the slot right here, and I can move that wiper around so I can have greater or lesser resistance on the tab that is connected to this wiper. Okay, so that's a variable resistor, a potentiometer. Here's another form of potentiometer that's commonly used for a volume control in an amplifier or in a radio. A resistor opposing the flow of direct current. A capacitor stores energy in an electrical field. Here's the schematic diagram for a capacitor. Here's a little sketch that shows what a capacitor in concept consists of. You have a plate connected to a wire. You have another plate connected to another wire. And in between those you have some kind of a dielectric, it's called, and that's another name for insulator. So it can be anything that doesn't conduct electricity. It can be air, it can be vacuum, it can be a piece of mica, it can be a piece of ceramic, a piece of glass, just anything that does not conduct electricity that keeps those two plates apart. Okay? And then there are a number of forms of capacitors. This is a ceramic capacitor, which is a very inexpensive form of capacitor. This is a more precise capacitor than ceramic, more expensive, and used in particular kinds of circuits where the precision is more important. These are electrolytic capacitors, which have a very high capacity, a very high ability to store electricity, and are used in power supply circuits and other places. Something you'll notice about an electrolytic capacitor is that, see here, they have a minus marked on this band here on the side of the case. What that means is that this wire right here next to that band is to be connected to the minus voltage side of the circuit. Okay, electrolytic capacitors are polarized capacitors. So if you're installing those, you need to pay attention to the polarity. And here they've marked the negative side, which is that wire right there. Here are some variable capacitors or adjustable capacitors. Here's a picture of a variable capacitor. And in this capacitor, it's air insulated. The dielectric is air. And when I turn the knob on this shaft right here, I can move these plates in and out of these plates here. And as I put more of these plates in between these plates, the capacity increases. The amount of capacitance increases. Okay? So I can adjust the capacitance that way. Here you can see it in a schematic form. Here are the fixed plates right here. Here are the movable plates on the shaft right here. And then here's a drawing of basically a similar thing to this. A couple of other ways to do this. This is a adjustable capacitor, variable capacitor, which has a little sheet of mica in here. And as I turn this screw, I move the plates closer together or farther apart. And I adjust the capacitance that way. The closer I put them, the greater the capacitance. Here's another one that has a flexible material, a flexible dielectric in between the plates. And if I squeeze on those, it puts the plates closer together and again increases the capacitance. Here's one that has one of the plates is actually in the form of a tube and the other plate's in the form of another tube that goes inside. So here I have my insulating dielectric element here, and as I move that inside the other tube, it increases the capacitance. The more of it that is opposing the other side there, the higher the capacitance.